In this lesson, we're actually going to use proofs in coordinate geometry to show that the theorems we've been using actually are correct. So we're going to begin with writing a coordinate proof to show the midpoint of the hypotenuse of a right triangle is equidistant to all three vertices. Now in order to begin this, we need to first establish what our triangle looks like and assign coordinates to those vertices. So easiest way to do this is going to be draw a first quadrant graph, and then on top of that we are going to place our triangle. And we're going to have the right angle be at the origin, and we're going to name some arbitrary points. Sorry, that line is not as straight as it should be, but let's work on this being a right triangle. So we have point O, which is at the origin. Its coordinates, of course, are 0, 0. We have, I'm going to call point E here, and its coordinates I'm going to call 0 because it's on the y-axis, 2B. I'm going to have point F out here. Its coordinates are going to be 2A, 0. The 0 here is because it's on the x-axis. And then I'm going to have my midpoint M. And what I need to do is first find what this midpoint is, and then establish the distances from that midpoint to the vertices. So let's begin with finding out what the coordinates of M are. Well, the midpoint is the coordinate of the average of my x's, so 0 plus 2a divided by 2, and then the sum of my y's, 2b plus 0 divided by 2. So this simplifies down to being the coordinates for m of 0 plus 2a is 2a, divided by 2 is just a. And then for the y part, 2b plus 0 is 2b, divided by 2 is b. So the midpoint's coordinates is AB. Next, I need to establish the distance from M to all three of the vertices. So let's begin by finding OM. Remember, distance is the square root of my vertical change squared and my horizontal change squared. So what is the vertical change going from O to M? Well, to go from 0 to A gives me a vertical change of A. And I will square that. Plus, now I need my horizontal change. So what is the change? Sorry, that was the horizontal change. Now I need my vertical change to go from 0 to B, and that distance is B. So I square that. So the distance from O to M is the square root of A squared plus B squared. Next, let's find the distance from E to M. And this will equal the square root of that horizontal change squared plus the vertical change squared. Well, horizontal change, do it correct this time, go from here, 0, to here, A. So that distance, we get 0 minus A, and we'll square that. And then our vertical change is to go from 2B to B. Well, that is 2B minus B. Now, if we simplify this, 0 minus A is negative A, and negative A squared is just A squared. A negative times a negative is positive. 2B minus B is 1B, and 1B squared is just B squared. So far we've established that OM and EM are of equal length. Let's check to make sure that FM is. So FM is equal to the square root of, again, our horizontal change squared plus our vertical change squared. This time our horizontal change from F to M, we're going from 2A to 1A. So we get 2A minus A. And then our vertical change will be from 0 to B, and that is 0 minus B. Simplifying this, 2A minus A is just A, so we end up with A squared. 0 minus B is negative B. Negative B squared. Negative times negative is positive, so we end up with B squared. All three lengths from the midpoint to the vertices are equidistant. So we have hereby proven this theorem to be true. Let's take a look at another one. Use coordinate geometry to prove theorem 5.1. Now, theorem 5.1 stated if a segment joins the midpoints of two sides of a triangle, and then is parallel to the third side and half as long. This was our mid-segment theorem. So we're going to follow the same way we just had. Going to establish our two axes and place on here a triangle in general terms that we can use. Now we are going to use the convenience of point O, the origin, 0, 0. And then I'm just going to draw a triangle and establish some general coordinates for my pieces. So at the top of my triangle, I'm going to call this T, and the bottom right, I'm going to call it P. Now the coordinates of P, I'm going to assign to be 2A, 0. It's on the x-axis, so the y value is 0. Now the coordinates for T, I'm going to establish as being 2B, 2C. Now the reason the 2's are used quite often is because that makes it possible to take half of it without dealing with fractions. Other numbers could be chosen just as well. This makes it convenient. So what we're going to have to do is, as the theorem states, find the midpoints of two sides, talk about it being parallel, and then half as long. So first, our midpoints. I'm going to find the midpoints here, which I'll call L, and here, which I will call R. Now, a little less writing because I have more things to prove, so the coordinates of L is going to be the average of my x's. So from 0 to 2b, the average is b, and the average of my y's. From 0 to 2c, the average is c. So the coordinates of L is just b, c. For R, I add the 2 together and divide by 2. So 2b plus 2a divided by 2 is just going to give me a plus b. Could just as equally say b plus a. And then from 2c to 0, the average is c. So I've found the midpoints. Now I need to show that line segment LR is parallel to line segment OP. So what is the slope of OP? Well, slope is our change of y divided by our change of x. Change of y from 0 to 0. Change of x, 2a minus 0. So we get 0 divided by 2a, which is just 0. Now my slope of LR, again change of y, so we'll go c minus c, divided by change of x, which is a plus b minus b. I end up with 0 divided by a, which is just 0. So we've established they're parallel because we have the same slope in both line segments. Next, we will find the length. The length of OP is going to be the square root of that horizontal change, 2a minus 0 squared, plus the vertical change, 0 minus 0 squared. So we get the square root of 2a squared plus 0 squared. Well, the square root and the square are inverse operations, so they will cancel each other out, and all we're left with, the length of OP is 2a. Next, let's find the length of LR. That is the square root of a plus b minus b squared plus vertical change, c minus c squared. Well, a plus b minus b is going to be just a, and then c minus c is 0, so we'll have plus 0. Square root of a squared is a. And here we have established that the length of that base, that third side, is twice as big as the length of the first side. So we have hereby proven Theorem 5.1 using coordinate geometry. So the theorems that we've had and the method for proving, you need to establish a general shape, assign those variable coordinates, and then run through your formulas and prove the pieces that are needed. Make sure you're ready to work with this and ready to prove some theorems.